I would like to welcome Krystian Gajdzica. I probably butchered that, but
Gajdzica.
Gajdzica, cool. Who's going to talk to us today about some inequalities for the restricted partition function. Please take it away, Krystian.
Thank you very much for introducing me. It's a great pleasure to me to give a talk about the theory of partition, more precisely about the restricted partition function during the student symposium this year. And well, at the beginning, let me recall everyone a definition of the most basic object from the theory of partition, namely just a partition. So if you have a non-negative integer n, then by a partition lambda of n, we mean each non-increasing sequence of positive integers lambda 1 up to lambda j, such that the sum of these elements equals n. We will further name these elements lambda 1 up to lambda j the parts of the partition lambda. So in particular, if we allow n to be equal 4, then we have the following possibilities to express 4 as sums of positive integers. And now one can ask, okay, we have a partition, so how many partitions do there exist for a given parameter n? In other words, we may define the partition function, which counts all the partition of n. This function is defined for all non-negative values of n, but actually we may extend the definition for all integers simply by assuming that p of n is 0 if n is negative. And it is also worth underlying here that if n equals 0, then p of 0 equals 1 because we have the empty sequence. So in particular, if we go back to our previous example, then we have that the p of 4 equals 5. Great. However, this is not the main object of my talk today. I wish to talk about the restricted partition function. So if you have the restricted partition function, we also need a restricted partition. So let us assume that k is a positive integer. For example, let k be equal to 6. And let us also assume that there is a weakly increasing sequence of positive integers, curly a. So let us assume that curly a is a sequence of consecutive positive integers such that each positive integer j appears in j distinct colors. Then by a restricted partition lambda of a non-negative integer n, so for n equals, if n equals 4, or n equals 4, for example, by a restricted partition lambda, we mean a partition of n such that the parts lambda n up to lambda j belong to the multiset which consists of the first k elements of the sequence curly a. So in our example, we look only on those partitions of n, which parts belong to the set which consists of 1 in black up to 3 in red. So we have the following possibilities. But it is a small ambiguity here, namely, okay, we have a weakly decreasing order of the parts of the summands actually, but in the middle of the example, we see that there is a 2 in blue plus 2 in black. So we also need to have 2 in black plus 2 in blue. And that is the case. We also demand that the two restricted partitions are considered the same if there is only a difference in the order of their parts. So in particular, 2 in blue plus 2 in black is the same as 2 in black plus 2 in blue. And if you have a restricted partition, now we can define the restricted partition function, which of course enumerates all restricted partitions of n. So in particular, in our previous example, we have that p curly a of 4, 6 equals 9. Great. So let us go to the first inequality related to the to my talk. It is the so-called Bassenrod-Ono inequality. Namely, in 2016, Bassenrod and Ono showed that the classical partition function satisfies the following inequality for all positive integers a and b under this conditions. And their proof is based on analytic behavior of the partition function. but it's also worth mentioning that there are another two proofs, as far as I know. The second one is in a combinatorial manner by Jajola and Nagy. And there is also a proof by induction on A and B by Heim and Nauhauser. And actually, the theorem of Bassenroth and Ono initiate a great research related to discovering similar inequalities for another variations of the partition function. So in particular for the restricted partition function. And that was the goal I wanted to achieve. And the theorem I was able to obtain says that if we assume that K is at least 2, and of course, as always, Carlia is a weakly increasing sequence of positive integers with the additional assumption that the greatest common divisor of the first K elements of this sequence equals 1, then we have a Bassenroth-Ono type inequality for the restricted partition function. The most important thing in this theorem is that it cannot be extended in a sense that we cannot omit any of the assumption appearing in the statement. Because if, for example, we assume that the greatest common divisor is strictly larger than 1, then there are infinitely many values of n for which the restricted partition function equals 0. So this inequality in particular cannot hold. My proof, similarly to the original proof of the Bassenroth-Ono inequality, is based on the asymptotic behavior of the restricted partition function. So here is the task for you. Maybe next time we meet, some of you will present a combinatorial proof of this fact. It would be very desired to see such a proof. So what about the idea of my proof? The idea is quite simple. Because in many cases, the restricted partition function is a very complicated function. The explicit formula for the restricted partition function is complicated. It is much more convenient to find, let us say, function f and g, such that f is strictly smaller than p of nk, and g is strictly larger than p of nk. And if we find such functions, then we just bound the left-hand side of this inequality from below and the right-hand side from above, and check under what condition on A and B the following inequality holds. In order to obtain these two functions, we need to know something more about the restricted partition function. And that is the theorem of Polishega and Neto from 1920s, which states that, well, the restricted partition function behaves like a polynomial of degree k-1, with the additional assumption that the greatest common divisor of a1 up to ak equals 1. We have that the leading coefficient of this polynomial is of this following form, and the remaining cases are or something like O, capital O of n to the power k-2. So our goal is shrink it to finding f and g of the following forms. So we would like to find real numbers capital C, such that, of course, f is strictly smaller than p of nk, and g is strictly larger than this number. And in order to find this constant, we may apply, for example, the theorem of Chimpos and Nikolaev from 2018, which gives us an explicit formula for the restricted partition function. As we see, it is quite complex formula. However, if we know some actually properties of the unsigned Stirling numbers of the first kind, then we are able to deduce the appropriate value of the parameter capital C from the previous slide. So as we see, the idea of the proof is quite easy, but the only problem might be to deal with this expression. Great. So the Bassenroth-Ono type inequality is the first inequality I wanted to talk today. However, there is a more intriguing inequality related to the related to the restricted partition function, namely the so-called log concavity of the restricted partition function. So let me recall everyone that we say that the sequence of real numbers, let us say Ci, is log concave if it satisfies the following condition for all n greater or equal than 2, or for all sufficiently large values of n. It turns out that the classical partition function is log concave for all n greater or equal than 26. So I asked myself whether the similar property holds for the restricted partition function. And the answer is it depends. Sometimes it's hold, sometimes it doesn't. It does not hold. So in order to gain some intuition, let us consider a few examples. And however, in order to make these examples slightly a bit more transparent, let us define the function capital delta, which is equal to the following difference. So in particular, if this function capital delta is positive for sufficiently large values of n, then the corresponding restricted partition function is log concave. Let us deal with the sequence from one of the previous slides. So that's the sequence of consecutive positive integers, and check and take a look on the graphs of the function capital delta for k equals 3 or 4. Well, in that cases, it seems that we do not have the log concavity of the restricted partition function. However, if we replace 3 or 4 by 5, 6, 7, etc., then magically we obtain that probably the restricted partition function is log concave for these parameters. So the question is, what should we assume about the multiset A1 up to AK in order to obtain the log concavity of the restricted partition function? Because let us observe that if k equals 4, then all of the assumption from the Bassenrod-Ono type inequality holds. K is greater or equal than 2, and the greatest common divisor of 1, 2, 2, and 3 equals 1. Great. So let us take a look on a bit more weighted example. Namely, let curly A be a sequence which consists of 5 2s at the beginning, and after that we have at least 3 3s, and further, actually whatever you like. In that case, if k is smaller or equal than 6, then once again we see that probably we do not have the log concavity for the restricted partition function. However, if k equals 7, then once again we do not have the log concave. Once again, we see that the restricted partition function probably cannot be log concave. But if k is at least 8, so we consider the multiset which consists of 5 2s and at least 3 3s, then we obtain that the corresponding restricted partition function seems to be log concave. So what about the theorem? The criteria which I was able to obtain says that, of course, if we have a weakly increasing sequence of positive integers, then we actually have two options. If k is either 2 or 3, then we need to assume that a1 equals a2 equals blah 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 equals ak equals 1. Or if k is at least 4, then it is enough to assume that the greatest common divisor of a, where a is each k minus 2 multisubset of the multiset a1 up to ak, is coprime. And with this additional assumption, we obtain that the restricted partition function is in fact log concave for sufficiently large values of n. Once again, the most important thing here is that we cannot extend this theorem in a sense that we cannot omit any of the assumption appearing in the statement. However, I strongly believe that this number appearing here, so the demands for n, so the demand on n can be reduced. So it might be much more, in my view, it might be a smaller number. Great. My proof, as in the case of the Bassenrod-Ono type inequality, is based on analytic behavior. So this is another task for you. Try to deal with this problem in a combinatorial manner. Great. Good. So let us take a look on a simple example, maybe related to this theorem. For example, if we take a sequence which consists only of ones, then it is well known that the corresponding restricted partition function is equal to the binomial coefficient of the following form. And in fact, one can easily observe that the the inequality 1 holds for all integers n and k greater or equal than 2. Good. So that is actually everything I wanted to say about the log concavity of the restricted partition function. And now I would like to say something about generalization of this inequality. Namely, we can also consider slightly to be more general version of this inequality. For example, the expression of the following form. And it turns out that under the same assumption on the multiset A1 up to AK, so that is this assumption which says every k minus 2 multisubset must be co-prime, it is enough to obtain the following inequality. And the most important thing here is that the exponent appearing in the denominator here cannot be replaced by any smaller number. However, the number appearing in the denominator might be replaced by a slightly larger number, which depends on the value of k. Actually, I do not remember the details now, so I'm sorry, but I do not remember. And this is, of course, only one inequality, but we can also consider the so-called strong log concavity of the restricted partition function. So in other words, we assume that we have a given positive integer m and check under what condition on A1 up to on the multiset A1 up to AK, the following inequality holds. And it turns out that once again, every k minus 2 multisubset must be co-prime. So that's the sufficient condition for this inequality. Of course, the demand for the value of n, the demand for the values of n is different in this case. However, the approach is effective also for this inequality. We can also deal with the following problem. And here we have two positive integers a and b. A is strictly larger than b. And we want to investigate whether the following inequality can hold. And once again, it turns out that under the same assumption on the multiset A1 up to AK from the previous slide, the following inequality holds for sufficiently large values of n. Great. So let us take a look on something on a slightly different example, namely the long balancedness of the restricted partition function. So this is the question about the log concavity of the function p of nk over n factorial. And in this case, it is enough to assume that every k minus 1 multisubset must be co-prime. So it is a little bit different. And the last one, the last inequality in this the last similar inequality is related to the log concavity of p of nk over n to the power alpha, where alpha is a positive real number. And up to this day, I only showed that this inequality holds for all alpha greater or equal than 1, but I strongly believe that it can be also shown for alpha between 0 and 1. Great. So, however, there are some more intricate questions about the restricted partition function. For example, the so-called higher order Turan inequality, namely the question whether the following identity holds for the restricted partition function. Of course, we need to replace Ci by the corresponding values of the restricted partition function. And what is a little bit interesting in this example is that my approach allowed me to show that this inequality holds for the restricted partition function if we assume that every k minus 6 multisubset of the multiset A1 up to AK is co-prime. But this is not the end. There is another intriguing question, namely the so-called the R log concavity of the restricted partition function. So that is related to the following sequences, namely we define recursively the sequence Qi of n by putting Q1 of n is just the value of the function capital delta of n plus 1, and Qi of n is of the following form. And we would like to ask whether there exists some positive integer m such that for all values of n strictly larger than this lambda m, all of these numbers are non-negative. And up to this day, I only examined that that the restricted partition function is 2 log concave under the assumption that every, once again, k minus 6 multi-subset must be co-prime. So as we see, I still have a lot of work to do. And finally, at the end of my talk, for anyone who would be interested in the theory of partitions, I hugely recommend the following two positions. And that's all I prepared for today. Thank you very much for your attention.
Thank you very much for a really great talk. Do we have any questions for Krystian? You can just unmute yourself if you want to ask a question. I had a quick question just to start it all off. So you talked about sort of you dangled the carrot of this idea of the combinatorial proofs of these things. And what I'm interested in that sense is, do you think there's existing framework which could be useful for solving this, or do you think it's sort of like, is it sort of completely out of bounds in some sense? Will it need sort of a completely sort of new approach in order to find a combinatorial proof for these things?
Oh, as far as I know, we actually do not need a very new approach, because in the case of the classical partition function, the proof of the theorem, let me go back to the slide. Okay, so this is the combinatorial proof of Alanazzi, Gagol, and Monaggi, is based on just simply finding an appropriate injection from the set of partitions appearing on the left-hand side of this inequality to the set of partition counted on the right-hand side, and this is actually the solution. So they discovered such an injection. So that is I believe that this is the appropriate way, or the way to
the right way to think about it.
Yeah,
the right
exactly.
way to think about it. Yeah. Okay. Interesting.
I see also a question in chat about the reason why Bassenrod-Ono inequality was proven so late. Well, that is because the log concavity, actually this result of DiSalvo and Pak, it is also a fun story, because the theorem of DiSalvo and Pak appeared in 2015, but Nicolas proved this fact in 1978, and the theorem of Nicolas was forgotten for a couple of years because it was written probably in French, and unfortunately that is the reason. And the work of DiSalvo and Pak was was a motivation to Bassenrod and Ono to discovering their inequality for the partition function. So the work of DiSalvo and Pak was actually the motivation for the Bassenrod and Ono to investigate the following inequality.
Excellent. Are there any more questions?
I had one.
Yep.
Krystian, apart from the restricted partition, that subset that you considered, the one that had the, I guess all of the Bassenrod-Ono type inequalities that we have here, the restricted partition function that we consider here, the parts, they are co-prime to each other, right? That's the condition, right? Are there any other kind of restricted partitions that have been considered by you or anyone else?
Oh, can you repeat slightly, a bit slowly? I'm sorry, I am not sure whether I understand you correctly. So you asked about. Okay.
Yeah. What I mean is the restricted partition functions, right? The subset that you have considered, the subset A that you have considered.
Yeah.
The parts there are co-prime to each other, right? That's the condition.
Yeah. So this you are talking about. Excuse me. You are talking about the assumption that the greatest common divisor of, well, A1 up to, let me say, go to this slide. well, no, it's not the direction. This is the assumption that the greatest common divisor of A1, AK equals 1.
Right. So are there any other conditions that people have considered over here?
Let us observe that this is very natural assumption. Let's observe that it's very natural assumption, because if the greatest common divisor is larger than 1, then there are infinitely many values. Then all values of n which are not congruent to 0 modulo this greatest common divisor cannot be expressed as a sum of these elements. So the restricted partition function takes 0 for all such n's. And in particular, if we take, for example, A, which is congruent to, let us say, I, which is not 0 modulo the greatest common divisor, and B, which is congruent to minus I modulo the greatest common divisor, then we have 0 on the left-hand side, but on the right-hand side, we may obtain a positive number. So that's a problem. And in the case, well, if so, as I said, we cannot find such a number like here, because there are infinitely many values for whose the peak of nk equals 0. So that's a problem here. So we cannot omit this assumption either in both the Boson-Roth type inequality and in the log concavity problem as well.
Okay, thank you.
Excellent. I think that's all we have time for in terms of questions. So would everyone like to join me in thanking the speaker again?